everyone. My name is Oleg Anastasyev. I've been in distributed systems development for a long time. Most interesting were several social networks. I started at DevClub.lv and eventually evolved into a larger social network with multi-million monthly active users. I developed one of the most highly loaded systems there. I use it to store likes data. This one processed more than 5 million requests. So the likes cluster processed more than 5 million requests per second. It was built using the stateful services approach we will discuss today in more detail. I went on within the development of one cloud, an in-house private cloud for a big tech company. These days it runs thousands of machines across multiple data centers and packs over 1 million CPU cores in total. It also employed the same efficiency and reliability principles. Now I build a technical platform for a zero-one tech company. We develop white label iGaming as a service Tooncane products. Our team is more than 1,000 engineers working remote and in offices located in various countries, including Riga. Currently we have 2 million active and almost 100 million individual users. Not much now, but we are growing fast across many regions of our clients and users. We are evolving our technical platform to meet the growth. We migrate from Amazon Web Services to our own hardware to have more predictable, cheaper, and reliable computing infrastructure. We also migrate from Node.js, which was historically used in the company, to more robust JVM, Java, and Kotlin platform. This is impossible without evolving to a high engineering culture, so we do just that too. So, let's start delving into efficiency. Let's take a messenger or chat service as an example of the efficient and reliable service we will build today. So in a typical messenger, a user could have a list of conversations or chats. An average user actively participates only in a limited subset of all conversations. Usually only 5% of conversations generate 95% of requests to the service. Most of the data messengers store are, well, messages. In this application, only up to 13 of freshest messages are seen, and so being requested from the messenger's data store. But these don't apply when getting the freshest message of each conversation rendered in next to chat names here. These messages are unlikely to be requested for a second time. When rendering the web UI, a freshest message is retrieved for each conversation and shown next to conversation name. Let's aim to store at least half of a trillion messages in, say, 5 billion conversations. This would take about 100 terabytes of data, and this new service should sustain more than 100,000 reads and tens of thousands writes per second with latencies of single millisecond scale. Every modern messenger should have full text search function, so when some text search is entered here, we'll find conversations and messages containing it. And this means that messages should be reiterated to build a search index. Messages are not only text. Here we can see some simplified message table with the conversation ID here, idea of the message within conversation, the author of the message type, finally the text of the message, and the list of final picture attachments to the message. So messages in our service can be represented with a table like this one. And messenger service must implement the following operations. Get messages, gets messages in the specified chat for defined user. It can return different messages for different viewers because of the selective message deletion, appropriateness filters, and so on. That's why the viewer is among parameters to this method. Most of requests to the messenger service come to this method, so it should work as fast as possible. Get last messages gets a single last message for the supplied list of chats to render the freshest message for each chat in the conversations list. This one is most heavy operation of the service. Multiple chats should be traversed to get the last message for each one. Add operation adds a new message to some conversation. Search is a full text search in the user's conversation, and index messages operation means an index for the search to use. Let's try to build this messenger service employing the model microservices architecture, of course. So users using their mobile phones or web browsers either directly or using some front-end servers communicate with messenger service. This messenger service runs application logic for the service. The application state or data is stored separately in the dedicated database store, and it is fault tolerant and highly available, of course. To achieve this, database could do some form of replication, so it's distributed, replicated, and so on. But let's leave it out of scope for a while for simplicity. That's it. Let's try to go live and see how the most frequent operation, get messages, could be implemented. To get this done, the query like this should be executed by the database. The problem here is that this query should be executed 100,000 times per second by the database, which generates some load to the service. Well, scaling is what microservices are all about. Let's start move instances. Let's start more instances of the service. And now we see that instances of the service generate more requests to the database. And now the database is overloaded. What's next? We could either scale the database or make use of the knowledge that only 5% of data are hit by a majority of requests. Let's cache some. And the database definitely have a cache we can configure. But it turns out that database cache is not efficient enough. It caches a lot of unused rows. This is because these operations of the service, they get last messages operation, and the messages indexing process are reading not only 5% of actively used conversations, but all 100% of conversations. These operations are very rare comparing to the get messages, but because they touch all conversations, all of them hit the database cache, flooding it with all those 95% of regular access useless to cache data. The database cache is typically restricted by few generic implementations. The least recently used algorithm is most popular here. Database cache typically cannot be adapted for application logic to control which data should be cached and which should never. So either we should throw much more memory to cache all this rarely accessed data, all data in the database cache, or we be able to implement an explicit cache management logic in the application. So only messages which should be cached are cached indeed. Let's introduce the memcache service for this purpose. This takes load of the database. When the load increases, we can scale memcaches independently from service instances and the database. This way we came to the typical modern service architecture many of us are familiar with. So let's delve into costs hidden in this in more detail. So the first is CPU cost of the marshalling and unmarshalling. This is the process of transforming the memory representation of an object to a data form suitable for storage or transmission. To make a single request to the memcache, the application logic marshals this request and its parameters. Then the memcache unmarshals this request to its own in-memory representation. After the memcache processes the request, it marshals the response. The application then unmarshals it, and these marshalling costs also apply to the application communication with the database. Intuitively, we tend to think that this cost is negligible. The right thing to do is to measure it for your exact system, of course. In this talk, I'll use measurements and results published in the excellent paper named Fast Key Wireless Stairs, an idea whose time has come and gone, from the group of researchers from Google and Stanford universities. Please read if you're interested in how these measurements was made. So, according to these measurements, this cost could add a fair amount to CPU load and can constitute almost a third to a median latency of the system. The second is the cost of overreads and overwrites. These are costs of reading or writing more data from the cache than it is necessary. If we store last 13 messages in the memcache packed into a single block for each conversation, to render this list with a single freshest message next to each conversation, we'd read a block containing all 13 messages of each conversation, marshal it, transfer it to application, and marshal it to individual 13 messages, and throw away 12 of them as useless except the freshest one. The same paper states that if only 10% of data is used from all the retrieved data, like we have here approximately, we can expect almost half of CPU and dramatic piece of the network traffic wasted by overreads. The third is the cost of network-related latency. Each request response pair to both the memcache and to the database introduce round-trip time latency, or RTT. The additional delay absorbed for moving the data over the network to or from the memcache and the database, and they can vary a lot depending on the size of the response. But the worst thing is that these latencies are then multiplied by the number of network requests the application logic makes to serve a single user's request. For the get last messages request, a separate request for messages of each conversation must be made to memcache, multiplying a single application request to tens or even hundreds of memcache requests. Well, as we can see, costs are high, but how can we lower them? Most of the load naturally fall to the memcache and it's linked to the application logic. So these costs are much more visible here. Most efforts in industry are spent on optimization of memcaches and they link to the application logic. For instance, Redis and Tarantul are trying to fight overrates by introducing data structure in the memcache, allowing application developers to request only the necessary subset of data. Netcache fights network latencies by introducing the in-network caching embedded into the network switching infrastructure. KV Direct is about to lower CPU costs by placing unmarshalling onto the network interface card internal processor. We'll try to optimize it from a bit different angle. These costs are introduced by the sole remote location of the application state, so we can get rid of them by moving the state closer to the application logic. This way, we come to the idea of stateful microservices. A stateful microservice combines the application logic with the custom in-memory store in the memory of the same single process, and so the network latency costs are not applicable here anymore. This in-memory store is custom. It has the application-specific logic implementation. This allows an application developer to implement a serious application logic without overreads. CPU costs of marshalling and unmarshalling could be eliminated or lowered significantly, selecting the appropriate application-specific data format for both components. Embedding distributed persistent store software to the same process eliminates same costs on the second leg of the architecture and allows us to easily integrate all components. Boards embedded and distributed next to each other could be a bit mind-blowing. What I mean here is that we embed the program code of the distributed store, so storage software runs within the same process. An instance of stateful service then becomes a usual node of distributed store. Participates in distributed node cluster, stores data on local machines persistent storage, and does all the necessary operations just like a dedicated store node could do. This way we've got a more efficient stateful microservice, and it always is more efficient than the same application implemented as stateless microservice because it has no more costs to pay for external location of the application state. Let's also see how the statefulness affects the fault tolerance of the service. For this, let's consider what distinct failure scenarios could be in the simple distributed system of two communicating participants, the client and the server. The client sends a request message, the server processes the request, and sends a response message back. The client can send a request and disappear from network. The server can disappear as well. They can crash or reboot, or their hardware can fail and hang. A request or response messages could be lost. The network is failing, buffers underflow, or either communication body. The server could time out, a response is sent beyond the defined time bounds. The invalid failure response, the server responds with a message that client can't understand. How could this happen? Easily. The server is running fresher version of the software, but the client runs obsolete one. And finally, the arbitrary or Byzantine failure. A party makes arbitrary messages at the arbitrary time. This could be some bad intention actions like DDoS attacks, it could be software bugs, and so on. So a total of 7 failure kinds are possible. Let's try to apply them both to stateless and stateful architectures. Let's take a look at stateless service first. A user sends a request message to the application service, and the service processes it, sending requests and getting responses from both the microservice, both the mail cache and the database over the network. So here we have pairs of, 2 pairs of the simplest distributed systems. The first one consisting of the microservice and the mail cache, and the second one, the microservice and the remote database. What makes things worse is that failures of the memcache and the database are not unrelated to each other. So we must consider how a failure to the memcache will affect part of operations working with the database and other way around. So a failure of the database affects data in the memcache. So these failures are bound to each other and must be explicitly addressed by application developer. So we have 7 failure scenarios here. Another 7 to address is on the database, and we have third simplest distributed systems here between the user and the Microsoft the microservice itself, with yet another 7 failures kinds to address. All of these failures are bound to each other, so an application developer must address all of them, plus their combinations when a failure in one component affects operations or state of another. This adds another complexity to the code, making such failure handling harder to implement and debug. Let's now take a look at the stateful architecture. There are the same 3 machines, but their layout would be different. The sharding scheme would be different as well. In a stateless setup, each of the 3 machines is responsible for some set of the keys. When going stateful, each of the machines is responsible only for the third of the original case set, each for its own distinct subset. A user communicates directly to each stateful service instance, making the same 3 pairs of communication parties. On each of them, the same 7 failure kinds are possible. The only difference is that these failures are unbound to each other and are alike to each other, because all 3 instances are implemented as identical components. So addressing failure scenarios here is easier. Such failure handling can be implemented uniformly for only one pair and will work the same way for all others. To further evaluate reliability, let's compare probabilities of the full downtime. For the stateless setup and the downtime of any component, the memcache, the database, or the service itself, leads to inaccessibility of all keys. So the probability of the service downtime for a keys from a full case set can be calculated like this. For a stateful setup, downtime of a single machine leads to inaccessibility for only a 1/3 of cases. Only when all 3 machines go down, each one with its own third part of key, there will be inaccessibility of a full key set. So the downtime probability for the full key set will be calculated like this. Which one is better is not obvious looking at these formulas, so let's try to evaluate them, these numbers. Let's assume probability of a single machine downtime is 1/10. This is very high probability, of course. In real life, they are much, much smaller than 1, but let's take this number for simplicity. Then we have these numbers for downtime probabilities. The smaller number is the better. We see that downtime probability for a stateful setup much smaller. In real life, people use replication to reduce downtime. So let's set up replicas for each of the components on the left. Installing the second replica reduces the downtime probability of a component by an order of magnitude. Now we have allocated 6 machines for stateless service. In this setup, is this setup more reliable than 3 machines from the right? Let's do our calculations with new numbers. Actually, no. failures are still bound to each other, so both replicas failure will still lead to downtime of the full key set. Let's try with 3 replicas for each component, and total of 9 machines against the same 3 on the right. Now, the same replication idea could be applied to the stateful setup as well. And this makes downtime probability of 1/3 of keys smaller than by an order of magnitude 2, and downtime probability of full key set by 3 orders. So we can see that the stateful microservice is more reliable. Okay, let's get to the implementation of the idea. So what to start from? We want our service implementation to be highly available, so a replication must be supported and consistency guarantees between the replicas must be defined. And we want our service to be scalable, so when load to our service increase, we could scale it by adding more instances. Now our application and its state are collocated, so we must implement resharding of the data state's data, newly added instances. All this could be implemented from scratch, but these parts are really hard to get right. Instead, let's find something ready to use. So let's choose among modern distributed databases. So first of all, let's decide which one we could embed. This database must be implemented in the programming language of the application logic, so make a code reuse simpler, avoid marshalling costs, and simplify an integration of components. It also must be open source, so necessary extensions of the database functionality could be implemented. We use Java for our applications. We had successful experience running Cassandra database, so we choose it as a database to embed. The first step to embedding Cassandra is launching it in the same JVM together with our application. Looking at startup scripts, you can easily find the Cassandra daemon class. It manages lifecycle of a Cassandra node. So all we have to do is include necessary libraries to the class path of our application and start the Cassandra node by this code. Cassandra.yaml here is a Cassandra standard configuration file. That's it. Now we have the database node running in the same process with our application. When started, it will read its configuration and join the Cassandra cluster just like if it was started by standard startup scripts. So as now, we have the state collocated to the application. Let's look how it changes the client request routine. So here we have our user. His name is Luke, and he is about to participate in the conversation, which key falls into some set key. Luke uses some front-end system for this, that's why I rounded him with the green rank terminal. For the stateless setup, there is no difference to which available instance to set a request to. The front-end could make a request to this instance or these instances. For all of these instances, cost of serving a request of a key from the set B is equal. Some network requests should be made to remote memcaches and databases to get the necessary application state. Contrary to stateful services, every instance has some part of key stored locally. Leftmost instance owns some set of keys A, second owns B, and the rightmost owns C. This way, the instance owning the set B does not have to make a network request for the data. It is either in the memory of the instance B process or can be read from its disks. Other instances cannot access this data locally and have to make network requests for it. The cost of processing these requests are higher because now should include costs associated with the marshalling and the network latency. So to make the processing effective, clients must route their requests directly to the instance owning necessary data and avoid routing their requests elsewhere. This is possible if clients are aware of the cluster topology. I mean information about states, data partitioning across cluster nodes. Such client routing could be implemented on the front-end system in the form of a library. This library route requests directly to nodes owning appropriate data partitions. So these nodes can process requests accessing the local data only. Data partitioning is sole responsibility of a database, and we have the Cassandra code embedded. Let's take a look how Cassandra partitions data. Every row in Cassandra has a primary key composed of two components. The partition key is used to determine the node owning the data, and the clustering key is used to define the order of rows within a single partition and has nothing to do with the data partitioning. Rows with non-matching partition keys fall into different partitions and could be owned by different nodes potentially. Rows with non-matching only clustering keys are in the same partition and will be placed to the same node ever. As in the messenger application, order of messages within the single conversation is important, but order of different conversations between each other is not important. We select the conversation ID as the partitioning key and the message ID as the clustering key. There are four main components in Cassandra code responsible for the data partitioning. The partitioner, given the partition key, calculates its token, usually applying some hash function to it. All possible token values are usually depicted as the ring. The partitioner is defined for the cluster once and can be changed in future. The whole ring is then split by token ranges. Mapping of ranges to primary nodes is stored in token metadata. And the final component is the replication strategy. It defines how to select nodes for secondary replicas of data and how many of them should be at all. Different replication strategies could be configured for different tables. That's it. This information is enough to get mapping of all data to cluster nodes by this simple code snippet. The endpoint map here is exactly this. It maps max token range value to all replica nodes addresses. Transferring this map to the client, the partitioner where routing can be easily implemented there. Also to consider that this topology is not constant and can change over the cluster lifetime. Some new nodes join the cluster, some old nodes leave, so this map refresh should be implemented in clients as well as dealing with clients with not yet refreshed stale mapping information. Various strategies we could choose here from what suits the system most. Well, clients now route a request for data to the right nodes. Let's look into how these nodes work with this data. So messages are stored in kind of this table, and we are about to implement get messages to get list of messages within a conversation. So it should execute a query like this one. To execute this query using the data stacks Cassandra client drivers, we should use a code like this. You can find this code on the Getting Started manual on their GitHub page. So in the first line, a connection to database cluster is established. The second line sends a query of the network and retrieves a result set. In third line, data is used then. And connection to a database cluster is closed, which is hidden in the final part of the try with the short statement. In real life, this could be a bit more complicated. Management of the connections, configurations can be retrieved from somewhere, some connection failure handler should be placed and so on. To execute the same query on the embedded Cassandra, we call this class execute method. It executes a query with specified consistency level, binding specified values to query parameters, and it returns a result set. Please note that this method is static. There is no connection information, no any cluster configuration passed in parameters. That's because the application code is working in context of a database it has embedded. No database to connect to. The instance is the database. Accordingly, messages for our getMessages implementation could be retrieved from the embedded database by this code. To add the message query like this should be executed and so on. Now we are ready to implement the custom in-memory message store. Let's recall the list of all requests the messenger server should implement. Only first three methods work with active conversations, so the new in-memory store should implement only these three. Others touch non-active data and can flood memory with the relevant roles as we already discussed. Let's implement getMessages first. A user named Leia opens the messenger and selects the conversation with Luke. I mean the front end sends the getMessages request for the last messages in this conversation. The application logic looks for the cached conversation in memory. Well, not there yet. Request messages from the embedded database, places the retrieved messages to the in-memory store, and returns them back to the front end. Feeling some disturbance in the force, Luke opens the messenger and uses his Jedi powers to route his get messages request to another yellow replica. The processing of the yellow replica is roughly the same. Messages are requested from a database, placed to the memory store, and returned back to Luke. Caring about Luke, Leia asks him to go for lunch. That means that we have the add request arrived to the blue replica. Application inserts this new message to the database and puts it to the in-memory store. And puts it to in-memory store. The state of the in-memory stored conversation is now like this. All done, the message is sent. Luke gets push on his phone, requests the fresh messages from the yellow replica, the application takes in-memory state of the conversation, and Luke gets stale state. No lunch. The galaxy is in great danger now. This is where data freshness plays important role. Adding the new message, blue replica should somehow notify other replicas about it so they can refresh their in-memory state. We could use the cluster topology information like we did before for client routing. Find out all the replicas which could possibly own this conversation and notify them about the new message by sending a special edit request. Then the application would place a new message to the local replicas in memory store. It is not stale anymore, and the galaxy is safe now, and it is not. The problem is that this edit request is being sent from one replica to others over the network. So all the failure kinds start to apply. So this edit request could be delivered only to some part of replicas. The rest of replicas could not have it delivered for a long time, depending on what happened to the particular replica. It could possibly crash to do a hardware failure for a long time. Let's take a look how Cassandra is about to handle the same situation. Executing the insert statement, it determines all updating conversational replica nodes, builds an update request, the mutation in terms of Cassandra, and tries to send it over the network. Because the messenger application and the Cassandra database now share the same process, this mutation message can be delivered to all replicas due to same failure kinds. In this case, Cassandra stores undelivered messages to the local persistent store. Whenever the yellow node is back online, all these stored mutation replicas are sent to it. This is called hinting. Usually, these hints are stored only for a limited amount of downtime. Otherwise, healthy nodes could run out of disk space, storing all to be delivered hints for a single node's prolonged downtime. So there are other ways of restoring a consistency between the replicas. They include the read repair, a process of comparing results returned by several replicas of the same query. If there are any inconsistencies detected, a mutation message is sent to the stable replica. And the final way is the streaming repair, a background batch heavy process of iterating and comparing through data stored on all replicas. Then mismatched ranges of data are exchanged between nodes. Because the volume to exchange could be large, new data are exchanged in form of a stable file, over the separate streaming connection instead of sending individual mutation messages. These consistency support methods are hard to implement in the debug. So it could be wise not to re-implement them all for the in-memory store. So what could be much easier is on receiving the fresh data by the database engine by either normal mutation, hint, read repair, or streaming repair. The database code could notify the application logic It then refreshes the in-memory state to include the fresh data. Consider the same case. The mutation message can be delivered, but not due to network failure, but because the yellow replica server is crashed and going to reboot its operating system. Its in-memory state is vanished. Now hints can help. Hints contain only the fresh data overseen by a rebooted node, but get messages needs all data lost from in-memory state and the fresh one. We could get the vanished state data by retrieving it all from the database. This retrieval could be performed for every conversation then, which was active before the replica rebooted. This could lead to the massive spike in amount of read queries right after the node is started. And because reads are served by a quorum of nodes in Cassandra, some network communication accounts for every read, there is a strong chance of catching a cascading failure of the whole cluster in this case. How to fix it? One could use the well-known strategy of having a periodic memory state snapshot to a persistent store combined with the write-ahead log of changes between two consecutive snapshots. But again, thanks to the embedded database code, we could avoid re-implementing this from scratch. We create the cache's key space with the local replication strategy. This strategy basically instructs Cassandra not to replicate data on cluster and store it only locally. Then we declare the messages snapshot table there, and whenever data is put to the in-memory store, it is being deleted from, it is being added to the store, and whenever data is evicted from the in-memory store, it is being deleted from this table. So this table now stores the copy of in-memory state. On node start, it loads this state by executing this simple select query, and this loads was state from the persistent local storage and hint supply, the fresh data, hint supply and the fresh data a bit later. This select query works fairly fast because it iterates sequentially over locally stored data, but still it takes some time. And this waiting time should be avoided, then restarting a node normally due to application, new version deployment, or maintenance. Loading state from the persistent storage can be avoided by using the shared memory to store the in-memory state. A shared memory is not cleared on the application restart until the machine is not rebooted. The simplest way to employ shared memory is to open this file. It is better to use a memory mapped file, of course, for Java, ready-to-use library. In Linux, the TMBFS file system usually is mounted under the dev SHM path. It's fine. We also use huge TLBFS subsystem with larger 2 MB pages. This allows to lower the number of TLB misses accessing shared memory and can conserve a bit of CPU cycles in heavy load cases. This makes things much faster. Starting the node with the shared memory map, only a quick sanity check is performed on startup now. The start became so fast that part of requests hit the just started replica before other replicas send all pending hints to it. And Luke could get stale data from the in-memory store again. This is because the hints delivery is asynchronous in Cassandra by design. Cassandra reads data from several quorum replicas every time, comparing results returned from every replica to others, so it can detect and throw away stale data before returning them to client. This heavy read makes the hinting an optional optimization, which is not strictly necessary for Cassandra for the consistency of the data. The messenger application gets 15 times more read requests than writes, so it is better not to use heavy reads for its consistency resolution. So right after initializing the in-memory state locally, we start the embedding Cassandra, cluster services, and waiting for hints to be delivered from health nodes. Only after all hints are played, the application is allowed to start to accept requests. This waiting looks like some kind of distributed coordination. We tried several strategies, and now we made use of the simplest one. The starting node periodically resends a check for unplayed hints request to all nodes. It waits then until all nodes confirm that they have no more hints to play, or go dead, and then suggests it is inconsistent. So, that's all about in-memory stores in today's talk. Let's have some summary. In stateful microservices, the in-memory store shares the same process with the application and the database node. It is custom, and application logic is implemented on it. Application objects are stored and manipulated in memory of the application service. This allows to avoid unnecessary costs associated with dedicated remote caches. Marshalling and unmarshalling of the reads are now easily avoidable. Network costs are now not applicable at all. The data freshness is the hard problem for remote caches to solve. We solve it by extending the embedded database engine code with mutation listeners. They allow us to add an application logic on a new or updating data, so we could guarantee that in-memory cached data is as fresh as it is in the database. The state loss problem should be addressed for any in-memory store. We solve it by replaying in-memory updates to the local database table and use shared memory to avoid loading a multi-gigabyte state from persistent store on every normal restart. In stateful services, in-memory caches could have the same consistency guarantee as the database. This is very hard to achieve for remote caches. Now, let's see how effective efficient the implementation of get last messages request processing could be. This request retrieves a single processed message for a list of users' conversations. To handle these requests, a list of messages has to be retrieved from many conversations. Different conversations could be owned by different application service instances. There are no single instance owning all data. These message lists should be retrieved mostly from inactive conversations. As we can see here on the screenshot, only one from many of conversations is selected and active. And this means that these conversations are absent from the in-memory store, and there is no point to load them there. Inactive conversation remains off most of the time. For stateless service architecture, we would have it implemented this way. The client calls the get last messages in the microservice, and then it would retrieve message lists from memcaches for every active conversation, and then from persistent database shards for inactive ones. Contrary, in stateful setup, there is no single instance to call. Any single instance is required to make a network request for all data, not owned by it locally, and this implies costs we are trying to avoid. The efficient way is to have get last messages implemented on all participants here. Microservices have their own implementation, and client has its own. Client's implementation uses the service cluster topology information and splits list of conversations, IDs, to several sublists. Each sublist contains only IDs of the conversations owned by a single service node. Then it selects the replicas for the first sublist and requests the last messages from it. The same happens for the rest of sublists. Service instances process these requests, each for its own subset of conversations, and return only a part of response to client. A client waits for the necessary partial responses from services, collects and merges them into a full response. It is essential to call all necessary replicas in parallel to keep duration of this processing short. Now we have to implement the last function for today's talk, the full text search. Whenever users enter some text in the search field, all messages across all these user conversations should be searched and shown in the conversations list view. Of course, scanning for text through all messages of all conversations is not feasible. A total data set of this messenger is over 100 terabytes, so even 1,000 machines cluster cannot make it fast enough. So we have to build an inverted index using, for example, Apache Lucene. A single large inverted index containing all conversations would not work. This is another interesting topic to discuss, but this is out of scope now, so you have to believe me here. Separate index per user would lead to unnecessary data duplication. Many users participate in many conversations, so we have to build an index only per every conversation. This index contains only messages of a single conversation. We build indexes upfront only for large conversations. For short ones, index can be built right before session. So let's start with straightforward implementation. Whenever a user adds a new message, they use Lucene index writer add document is called to index it. And then we call Lucene to commit index. This would not work. Too often commits leads to too often merges of Lucene index segments. These merges are both CPU and disk expensive operations. Contrary, do not calling index writer commit lead to too many open indexes because a single server's instance adds thousands of messages every second to multiple conversations. This could be too much memory. A good solution here would be some background process. This process would preliminarily merge new messages of a single conversation into a single collection as soon as messages are arriving, but not too often, to keep the size of these batches moderate. And Cassandra has such a background process named compaction. If you wish to know about this process in more detail, here's a link to read in the footer of the slide. In short, compaction merges different generations of data flushed at different time to persistent storage. Compaction is necessary for Cassandra to keep its data structure optimized. Compaction iterates over data to merge, always in order defined by row keys. A single conversation is iterated at a time. Messages of a single conversation are iterated in order of their IDs. Compaction is managed by the class named Compaction Manager. We could extend it to call some listener interface, which we implement in the application, to call necessary Lucene indexing. Well, now the stateful service can do the low overhead, massive data processing. This processing could be used in many other cases when iterating on a full data set is necessary by an application. This is the last crazy trick for today, but not the very last of all the possibilities. What I wanted to illustrate here that is embedding the database software allows for tighter integration of the application and the database. Allows to extend the database in the ways necessary for the application and allows for even more cost reduction across many aspects, not only related to request processing. So, we are at the last section of today's course, the production operations of stateful services. From the operations perspective, stateful services also have their own particularities. Let's look into them. The first problem to discuss is longer deployments. This is because the longer start time of the stateful service. This is because stateful service embeds the database. The database has to perform a persistent data initialization at startup. The initialization time is mainly bound by the speed of persistent storage, speed and volume of write-ahead logs. Speed and volume of write-ahead logs to replay. Another thing to wait for the in-memory storage loading for the last state from the messages snapshot table we discussed today. This time is bound by the size of state to load, frequency of change, and eviction events. The CPU power, the number of key collisions, this could last for minutes and even tens of minutes. The consistency wait time. We should wait for hints to be replayed by other nodes. This time depends on the number of skip implementations. So if the deployment process stops and then start instances one by one, the total deployment time is proportional to the total number of instances and could easily last for a day for several hundred instant deployments. So, to mitigate this, the deployment process should be not sequential but parallel, deploying multiple instances at once within a single availability zone. Our deployment process, for example, deploys a single instance first to make sure that new version is not broken. and the rest of instances of the zone deployed in parallel. Instances in the rest of zones deploy in parallel at once. This way, total deployment time remains constant regardless of the total instance count and depends on the zone's count. The second problem is we restart database nodes more often. Well, we embedded the database to the application service node, so we restart the database node in each availability zone. Each time we have to deploy a new application version. Should we mitigate this? Actually, no. This is not a problem for today's fail-first databases like Cassandra or Oleg. This deployment actually tests an availability zone outage on every deployment in the controlled environment and during the work hours. So bugs in zone outage handling could be detected and fixed early before the real outage occurs. The third problem is longer scale out. This is because data is collocated with applications, so to add more instances to the application, data should be resharded, physically moved over the network to the newly added instances. This problem is not specifically unique to stateful services. Stateless services require resharding to scale out the database and memcache components too. Still, could avoid resharding for application logically generated CPU or network-bound nodes. This urgent needs for the CPU or network consumption by application logic is often related to some new functionality. To mitigate this, a capacity planning should be in place. This longer time should be taken into consideration, so an application could be scaled out before the load spike hits. To mitigate load spikes rooted in a new application functionality, feature flags could be used for a new code, so they could be employed to cut off the problem code. We also can shorten the data resharding time by deploying more smaller instances instead of deploying less larger ones. This way, resharding process could take advantage of parallelization. The appropriate automation should be in place then to keep the operations easier. There could be cases when application sourced load spikes are unpredictable, externally rooted, highly volatile, and the only solution is to have fast auto-scale, which implies no resharding is possible. These measures may not help, and sticking with stateless microservices architecture may be a better approach. This is somewhat the development of the problem I mentioned on the previous slide. This problem applies only to applications which consumption of one machine resource is much higher than others. Imagine a service which needs high amounts of CPU to do complex calculations or over some small amounts of data. Such an application will consume all available CPU on the machine, leaving disks underutilized. It is impossible to install a fraction of disk into my machine, so underutilized resources of the disk will be wasted. On the contrary, we could imagine an archive service doing very little processing of large amounts of data. Disks of this service would be full of data, but machine's CPU would be idle. Stateless services allow each component to be scaled individually, so these imbalances could be mitigated by scaling out stateless service components more for the first application and scaling out the database for archive one. For stateful, this is not possible. State and application logic are collocated. These imbalances could be mitigated by employing containers and orchestration management systems. They aim to balance resource utilization across the fleet of my machines automatically, allocating different containers with different resource and consumption properties, keeping distinct resources utilized uniformly. A container with high CPU and low disk consumption would be highly likely be collocated by orchestrator into the same machine with the container having low CPU and high disk resource consumption. This would keep resources consumption of the hardware fleet leveled automatically across the organization. We use internally developed one cloud orchestrator for this, but there are several others possible. Kubernetes is one of the popular nowadays, but there are others as well. On the bright side, the diagnostics and support of a stateful service are easier than for stateless services. Because the application logic, the in-memory storage, and the database share the same process, it is much easier to diagnose and debug. Setting a breakpoint in somewhere in the application logic, one could easily track down the problem to the root of internals of the database and then even down to the operating system kernel. Running the profiler, one could track down performance problems more easily. Here you can see, for example, profiler run on a stateful service showing flame graph of the CPU time span from the application code here down to in-memory storage, stack traces, and the database engine operations here, as well as down to kernel space here. For stateless services, a Memcache and database runs on remote processes. Profiling and debugging an application often cannot show the root problem. Running separate profilers on the main cache and a database can show the application context. Most of stack traces start somewhere on network dispatcher, hiding the maybe root problem of the application-specific information. So diagnostics are often end up on custom database diagnostic tools or never random guesses if tools are inadequate and doesn't provide necessary details. And the final slide of my talk, stateful microservices are more effective and reliable, and application logic shares its cache and database in the same process. This way we avoid marshalling and network implied costs. The custom implementation of in-memory store avoids overhead costs. Stateful services have an in-memory state consistent with its database state, which is hardly achievable with remote caches. This is not so hard to implement having embedded modern distributed file-first database. Stateless microservices was invented more than a decade ago. Problems to which stateless was aimed for could be solved now in new ways. There is a lot of progress during the last years in distributed databases with seamless auto-sharing support, designed to be file-first from the ground up. Containers and orchestration systems are good at the process isolation, and the hardware machines automatic utilization leveling allow us to avoid externalizing an application in memory and persistent states in remote systems and open the road to build more efficient and reliable services. That's it. Thank you.
How much did you actually save on these costs? Because now you have analyzed your resources.
Actually, this was implemented in the likes cluster system first. The problem is that the previous solution were using the classic stateful approach just can't handle at all. So we implemented it first on the likes cluster, and it is running up to today, as I know. So this is just works. Just works much more efficiently than. And actually, there are a lot of services of the social networks I know about are built using exactly this pattern. Mostly because there are a lot of high load, a lot of requests per second going on the infrastructure to traverse your social graph and get all the information from the all parts of the social network. So that they should work as efficiently as and reliable as possible. So this cluster, which serves the 5 million requests per second, is built exactly using this pattern.
Maybe I missed something, but does it mean that every node has its own copy of the whole database?
No. Because we are using some kind of distributed database like Cassandra, the Cassandra partitions data across the cluster of nodes automatically. But, almost all of today's databases have auto-sharding built in. Only very old ones like MySQL and Postgres and Oracle are designed in the way to store all the data set on a single machine. This is not feasible today. So if you take whatever else, Cassandra or
Mongo. Cockroach.
not Mongo, please. they have problems with data consistency historically and up to today. Cassandra or Yugabyte or Cockroach or what shit was called.
CodeDB, no?
Where is the implementation of Cassandra in C? I don't remember. It's Scylla. Or Scylla, or what else? Foundation DB, for example, is also built to auto-sharding possibilities. There are a lot of them nowadays. So if you, the last time in the modern time, there are few distributed databases which even support the ACID transactions across the distributed cluster which are fast enough. Like Yugabyte, for example, works good for if you need ACID transaction. Cassandra does not provide ACID transactions. This is eventually consistent process. Scylla is also eventually consistent database. Foundation DB, I don't remember.
I have a question.
Mm-hmm.
So, if I understand it correctly, so you shard by conversations, right?
Yep.
So, are there issues perhaps when users are massively geographically distributed? Like one is on one continent and other is in other continent, and both are supposedly counting just one instance, no, one set of instances on one location, one data center.
Yes, there could be, for example, generally yes, they will hit their requests on a single instance if they want the consistent copy of the data. There is no way to make copy consistent. Or to one of the replicas. If we place replicas using the Cassandra in one data center, in another data center, we have consistent replicas there, so we can call any of replica of the conversation. But there are cases that there are so many people in the conversation, say tens or even hundreds of thousands of participants, then no replicas can handle the load. Then there is a strategy called fan out. These conversations this is application logic. This is not database logic. This is application logic which decides that this conversation should fan out, so it places the copy of the conversation on other replicas under another IDs, and there are mapping between the original ID and the fan out IDs, so you can distribute load across the several instances. But this actually works when more than 100,000 participants are in the single conversation.
I have just a small remark about the previous discussion about ACID transactions. Cassandra 5.0 claims to have As transactions along the vector search.
Nobody seen them.
Not yet. It's production ready, but nobody break.
They claim for recent transactions for the last 5 years, and nobody's seen these transactions in Cassandra yet in production.
Chocolate time?